Okay. Let me continue to what I have said. Okay. Uh, and let me do this one. Okay. Uh, okay. If you have any questions, don't just ask. Okay. Don't be hesitate. And I hope I'm glad that some of you uh after the class and came to me, then ask some of your questions, okay, which is very good, okay. And don't be too nervous at the beginning, since this is just, we are just, new hands, okay, no problem with it, okay, all right. And okay, any other questions which you would like to ask? Okay, the one I just have this equation, okay. And if I wanted to have the graph, okay, for this equation, I can use quick and use the graph. I'm sorry. I think I need to view. Huh? No, I'm sorry. I need to go back my data. Then, okay, I'll go back to here. Then I like to see the graph. And quick. There's a graph here and y and x, right? And I choose the scatter. What I have to do it here, I just have to choose the regression line, okay, in order to have the lines with me. And I hit OK. Okay. Okay. Here's the diagram with dots and the estimation line. Okay. All right. So any questions about this one? Okay. Uh, you may like to also see okay, let me show something about my okay, let me say something about it here. Okay, I think I have already shown that and here I have this output. Okay, I just showed this output, how to work with this output, right? Okay, then what else I have to say? Okay, and I have this chart. Okay, and how well does the equation work? How well does this equation work? Okay, if you wanted to answer these questions, okay, we need to calculate the residual, okay, and I already have this residual, right? So look at this residual. Story. This is the one. Delete the graph, yes. And no. Oh, sorry. Where is mine? Okay, look at the residuals. Okay, and Look at all those residuals. This is exactly of what I have from our textbook. Okay, according to the game, okay, the rule of the game, if the predictions, the predictions is within, I think it's within 10 pounds. Okay, let me see whether it is within 10 pounds. Okay, it's within 10 pounds, you will gain $2. And if outside the 10 pounds, either positive or negative, okay, you'll lose $3. So let's see. According to these residuals, most of them are within 10, positive 10 and negative 10. Then we do have three numbers, which is the difference. The residual is 18 point something. Okay, 2 positive and 1 negative, and which lost $3. So if you sum them together, and you'll win $25. So it means that if you set up the regression equation, you have this data, you set up this regression, okay, you will, for these 20 persons, okay, 3 out of 20, okay, 3 out of 20 are outside the range. In other words, is if I would say that maybe it's pretty accurate, right? So therefore, you are able to gain $25 according to this regression. So is it a good equation? I think so. Okay. Okay. Then if you turn to the exercise of this book, okay, turn to question number 5 on page 44. Okay, so I like to ask some of the questions, which is some of them, is from the exercise number 5 too. Okay, so for the first question, so I can ask that if we measure the height of a male, all this, by the way, this data is for all the males, okay? Because if you set up the equation, the relationship between height and weight, and I think it will be different, either is for male or for female, right? Okay, so this data is all for males, okay? So measure the height of a male friends and plug it into equation 1.19. Does the 1.19, I think this is the estimated regression. Does the equation come within 10 pounds? If not, do you think you see why? And why does the estimated equation predict the same weight for all males of the same height when it is obvious that all males of the same height do not weigh the same? Understand what I'm saying here? Why does the estimated equation predict the same weight for all males of the same height when it is obvious that all males of the same height do not weigh the same? So, for example, according to our data, okay, let me show this data, okay. We're using the same height. We're using the height to predict the weight. So, for example, I'm just taking number 5 and number 9 as an example. For this male, the height is 10, means there's 5 feet and 10 inches. And number 9 is also 5 feet with 10 inches. And the weight for number 5 is 162 pounds, and this one is 170. Okay, so that's what we're saying, that and actually this is the residual for this one is negative, and this one is for positive. Do you see that? So in other words, if I draw the line, if I have this one, this is weight, this is height. This means that the line is something like this one. So if I have the height is 10 inches. Okay, so for example, here is talking about 10 inches. Okay, I have two observation, two males. One is above the line, the other one is below the line. So for this one, there's a positive residuals, which is 2.8. This is the difference. This is 2.8. And for this one is negative. So I have to put this one a little bit lower. So for this two dots, the prediction is same as 167.2, right? So the prediction is well, actually this one is 170 pounds, and this one is 162 pounds. So the original data, it can be with the same X variables, it can be different Y variables. The Y variables can be different, the value can be different. Okay, so this is reality, right? It can happen. Okay? So this is what I'm trying to, we need to think about it. Okay? Why does the estimated equation predict the same weight for all males of the same height when it is obvious that all males of the same height do not weigh the same? Since it is the estimation line, at given some X point, I will give just one estimations, but actually the data can be either above it or lower than it. Okay? All right. Any other questions we need to thinking about it? Look over the sample with the thought that it might not be randomly drawn. Here we are really thinking about, when we collect the data, it should be the random sample. Okay, but we didn't know how do they collect the data. Okay, so it might not be randomly drawn. So does the sample look abnormal in any way? And if the sample is not random, would this have an effect on the regression result and estimated weights? Maybe, right? If it is not random sample, then it should have some effect on the regression result. Okay. Maybe they just, since we wanted to set up a relationship between the weight and the height, okay, we should be able to have the data which represent the populations. Okay, if it cannot represent the population, and this regression line, actually is just from the data set. Okay, so whatever you collect, they will get a result according to the to the sample you have. Okay, so random factor is also important to have a good representative sample of the population. All right, so anything else? Think of at least one other factors besides height that might a good choice as a variable in the weight and height equation. How would you go about obtaining the data for this variable? What would the expected sign of the variable's coefficient if the variable were added to the equation? Do you think about any other variables, since this one is just only based on the height to predict the weight? Any other than height, any other variables other than height can be added to this equation in order to have better estimation for a person's weight? There's no one answer, right? There's no one answer. Can you think about any of the factors? Anyone else? Anyone can say something about it?
Can you hear me? Hello.
Well, this is from other class. This is not from me. Huh? Oh, okay. I'm sorry. Oh, I didn't notice that. Okay. Okay. Would you like to say something about it? How do I call you? Actually, I don't know how to call you. Is Edwin?
Yeah, it's me. You can say
Edwin?
Edwin.
Do I call you Edwin in the class?
Well, if you want.
Or something you like to be called?
Evan is great. If you can pronounce it.
Huh? Edwin?
Evan.
Huh? Excuse me. Evan. Am I right?
Yeah, exactly.
Evan. Okay. So I'll call you Evan. Okay, please, Evan.
So body fat is actually influenced by age, especially when men and women are over 45 and 50. Well, it depends, of course, on the ethnic group you belong to, but whatever, you tend to have you have a higher body fat when you grow older, and you have less muscle mass. So to some extent, that influences the weight, and also some people tend to become fat or skinny during their lifetime, because, for instance, my father went from maybe 90 kilograms to 100 because of some things that happened in his life. And so from one age to another, you can change your body weight.
Okay, so what variables do you like to add in this equation?
Well, the age of the participant in the sample, that could be some indicator also.
Huh? Excuse me, I don't hear it very clearly. What variables? Age? You mean age?
Yes.
Oh, okay. So we add the variable called age, and you're just talking about that maybe after. Did you say something about 45 years old? Did you say something about that?
There's a lot of things. For instance, amongst men population, when you grew up, the testosterone levels also highs up with you, and so you tend to have more muscle mass. Around 30, your bones tend to grow more dense. So all that adds to body weight without even changing your nutrition. And so and that also plays in with woman body and metabolism. So when you grew older, for instance, from your 20 to your 70s, your body mass just changed by itself. Your body weight, sorry, that changes by itself because of, well, your body growing older.
Okay. Thank you very much. Actually, this example is all for males. Okay. So what you are saying that maybe we can add one more variables called age.
Yeah.
Okay. Okay. Then maybe it makes sense, right? Okay. Okay. What May say is if we just use the age as another variable, and maybe we can, set up some of the limits or something to differentiate either above this age or below some sort of age. Maybe, I don't know which age we should put it in, maybe 50 or something. If you're getting older, maybe it's easy to gain weight, even you eat the same food. Okay. So yes, it is good idea. So either we put the age, but we put some limits on it. Maybe something like this one. If the age over 50 or the age below 50, something like this one. Okay, good.
I would say like age between 10 and 20, then between 20 and 30, and then between 30 and 50, and then after 50. But
you see,
too much limits, then yeah, maybe just over 55.
It's more details.
Well, I don't want to make things complex for nothing, so well, maybe.
Yeah, okay. Yeah,
wait.
Understand it. Okay, all right. So, this is just the way we have to be, train ourselves to think about it. Okay, and in this case, since we're just using one single x variables, so it can be many other variables. So just like either Edwin or the May say that age have something to do with the weight. Okay. And what I'm thinking is, how about if you do the exercise or not? Right? If you have regularly do the exercise, then maybe they'll affect the weight. So either we will ask the question that whether you do regularly exercise, right? I think that will affect the weight too. Okay, so either one of them, we can train ourselves to thinking about actually in reality, it's not that simple. Just only use one x variables will affect the y variable. All right. Anything else? Let me think.
Nutrition, what you eat, of course, is maybe the main factor of weight or losing.
Yeah, that's right. Okay. All right. And anything else? All right. Let me go back to the examples here. We're just saying that we do have three. Okay, we have the three datas, okay, which is outside the 10 pound, the range of 10 pounds. Okay, if these three persons outliers, what do we mean by outliers is mean really abnormal. Okay, so in that case, if okay, if this is all randomly chosen people, okay, and if it is all the numbers are correct, okay, it is no reason to change the data set. Okay, but in some cases, if you happen to know that some of the data is not correct. Okay, I'm not saying that you can do that always. Okay, make sure the data is correct first in order to change or, manage the data. When I say manage data, it always is in bad side. I mean, it's not good. It's not a good idea. Okay, make sure your data is correct. Okay, if you can make sure that data is correct, then just use the original data and do all the regression and do all the estimation. I just like to say that maybe you can try, at home. Okay, without this one, so you eliminate 3 persons. There's a 2 here. Okay, and there's a 1 here. Delete these 3 observations and make the estimation again and see what happened. Since you can use the new estimation equation and do the residuals and see whether you can earn more. If it is, maybe, that's even better. I don't know. So you can go back home and try, delete these 3 observations and work all this estimation again and see the result. Okay, try it at home. I don't think I have time to do it here. Okay, all right. Anything else I like to say? Well, I think that's what I want to say for this example. Okay, then there's another example in 1.5 section. So there's another example. I'm going to show that example again. Okay, which is on page 38. Okay, look at this examples. Do I have this one here? All right. Okay, this is the example on the book on page 38 to 39. Okay, and this is about the price of the house. Okay, and let's see. How come there's so many things? Okay, and if we set up a theoretical simple regression models, Y variable is the house price, and the measurement units is in $1,000, and X variable is the house size in square feet. Square feet. I think in some of the countries using, maybe many of the countries using square feet to measure the house size, but in Taiwan we're using another measurement unit. Okay, it's different, but here the house size is measured in square feet, and Y variables is in $1,000. Okay, so if I have the relationship between the price, the house of the price, and the size. Okay, what's the relationship between this, the X variables and Y variables? Usually the bigger house, the higher the price, usually. So, I mean, maybe theoretically or, we expect the positive relationship. So we'll expect the beta 1 is positive. the number is positive. Okay, and unfortunately, in these examples, we don't have any data set provided in the textbook. Okay, but we will see the result of what the result have done. Okay, and one thing we like to mention that in this example, all this data, I mean, this all local houses were collected, and this house were sold within last few weeks. Okay, and in fact, we wanted to build a regression model of sales price of a house as a function of their sizes. And we call this kind of data set is called cross-sectional data. Okay, the name of cross-sectional means that all of the observations are from the same point in time and represent different houses. When we say same point in time, here, the same point, it doesn't mean exactly the same time, is within a few weeks. Okay, we can consider it a cross-sectional data. Or maybe, let me use the examples. If we want to, do some survey, usually you can, nowadays, maybe you can put on the internet, okay? And you have some 1 month and asked anyone wanted to answer the survey, right? So within this 1 month, as long as there's anyone do the survey, then you collect the data. So all this data is what we say from the same point in time, not the particular day, but just within a month, maybe. Okay, but if you are checking with the relationship between the stock price of some characteristic of the company, okay, in that case, what do you collect? If you say, I want to collect all listed companies, okay, so at the end of the year, so we do collect the data from the date of December 31st. The stock price is at the end of the year, means the stock price of on December 31st. Okay, the stock price from December 31st. And in that case, the stock price is what we call at the same time. Okay, this is all say, this is, called cross-sectional data. You collect all the listed companies. So all the listed companies is represent the different company, but their stock price at the end of the year. So which is also called cross-sectional data. And another data we call it time series data. Okay, time series data means what? Means one certain company with maybe 30 years stock price, annual end of year stock price for the past 30 years. So one particular units, one particular companies. So this is called time series data. Okay, and this semester, what we are working with, the data is all cross-sectional data. And, we will talk about time series data in the next semester for the other rest of the chapters of this textbook. Okay, so for this semester's all cross-sectional data. And this is, I want to mention it, okay? All right, and look at this relationship. Okay, this is the equation 1.20. Okay, this is called, look at this one is called relationship, population's relationship with the epsilon. And this is called estimated regression. So actually there's a head on it. No, when I put a head on it, it's already, it's already misleading, okay? And this is, after I have the data, then this beta 0 is 40, and beta 1 is this number, 0.138, okay? And since this is positive, so it really shows the positive relationship between the size and the price. Okay, now we have number of observation is 43. Does anybody want to explain it to me? How to explain the 0.138? How to explain these numbers? Remember, the size is in square feet and the price is in $1,000. Does anybody want to answer this 0.38? What's the meaning of it? Anybody want to try? Okay, this means that if the house, the size of the house increase by 1 square feet, the house of the price will increase by $138. Although this is $1,000, you can say $0.138,000, but nobody say like that way, right? You don't understand what you mean by $0.138,000. Is actually is $138, and it also make more sense. It's not just say, 1 square feet. Does anybody care your house size is, bigger than one square feet? Maybe if I call it is, if you increase by 100 square feet, then the price of the house will increase by, in this case, is $13,800, right? Because here is 100, so I have two decimal places here. Okay, so if I put 100, then it turns out to be 13.8. So in this case, I can say if the house size increased by 100 square feet, and the price of the house will increase by $13,800. Okay, all right. It's important to you to understand it. Okay. Anything else? Okay. So here I'm saying that the slope coefficient means that if increased by 1 square foot, price will increase by $0.38,000. It means $138. And how about the intercept? I think this is important here. Okay. How do you explain the $40? The intercept. Mathematically, okay, the intercept or the constant means when x variables equal to 0, right? So what do you mean by the house size is 0? What does that mean? Does it make sense? No, it is not. It is not make sense. It doesn't have any sense at all, right? What do you mean by the size of the house is 0? So whenever the 0 doesn't make sense in the original data set, then the intercept, mathematically, we can explain it. But in reality, this 30, this 40 doesn't make any sense at all. So we don't explain it. So when do you have to explain the intercept? Is when the x variables, the 0 of the x variables makes sense. Then it is able to interpret the intercept or constant. Otherwise, the intercept or constant doesn't make any sense. And most of the reality, I mean, in business world, okay, in business world, if all these x variables are quantitative variables, usually the intercept doesn't make any sense at all. Okay, but mathematically, it exists. Okay. All right, so this is what I'm saying here, that the intercept means the house price equals to $40,000 when size equal to 0, which has no economic sense at all. Okay, mathematically, it should exist over there, but economics, it doesn't make any sense. Okay, look at these equations. 1.22, which is from the exercise number 4. Okay, if you look at the book, exercise number 4, equation 1.22. Okay, using the same data, but what's the difference between 1.22 and 1.21? Look at this one. This is 1.21, right? And this is 1.22. What's the difference between this one? Look at carefully. I think it's hard to look at using the PPT. You can check with your textbook. Look at the equation 1.21 and 1.22. Tell me the difference between these two variables, these two equations. What's the difference? Did you see the difference? They're using X and Y and X, right? Here using the size as an Y and the price as an X. So I like to say that reverse the X variables and Y variables. Really is a big deal. So in regression analysis, make sure you know that what is X variable and what is Y variables. If you put it upside down, you consider Y as an X and an Y. The equation output will be totally different. So you see the difference and you see the importance, right? So make sure in regression analysis, make sure what is the Y variables you're talking about and what is the X variable. So in the section 1.5, where we wanted to predict the house price using the house size. In this case, house price should be the Y variable and house size should be the X variable instead of like this. this is really upside down, reversed. And you see this numbers and this intercept, in this intercept and the slope is all different. Okay? All right, anything else? And one thing I like to go back to these examples is the measurement unit. Okay, in this case, I'm using price. The measurement units is $1,000. Okay, if my original data, the measurement units is changing as a dollars instead of $1,000, what will happen to this equation? If I'm using $1,000, what will happen to the site, the intercept? Anybody want to say something about it? So in this case, if my price is 1 in $1,000, then it turned out to be 1,000 as I measurement in dollars, right? So all the Y variables can multiply 1,000. All the numbers for original $1,000 measurement unit. If I change it to dollars, then it can be, it should multiply 1,000. So all the number is different. In that case, how does all this constant or intercept and the slope changes? Does anybody can answer the questions? Just using the example, I just say that since it is, 1 square feet, okay, it turned out to be this $0.138,000. If it is dollars, it turned out to be 138 instead of 0.138, right? So if I multiply 1,000 here, then according to mathematically, the coefficient will multiply by 1,000 also, in order to match the original estimation. Anybody understand what I'm saying here? Okay, think about it. Or maybe, go back home and try to use your data and change the measurement unit, okay, and see how the equation or the estimation result coming from, or you will get a different result, right? And in that case, how does all this coefficient changed? If I change the measurement units, I think this is a good question to ask, okay? So today, I already finished chapter 1. And what I want to announce is 2 weeks from today, which is October the 6th, okay? We will have the first assignment due, okay? I'd like all of you to answer the question of exercise number 8. And this one, please, you can do the preparation, and the data set is from rate 1. You can get it from our data set. Okay. And those you haven't grouped as an, put your name on the group, please do that. Okay. So we will have assignment due on October the 6th. Okay. I think that's for today. Let me stop the recording. So do you all hear me on the Teams? The two students from on the Teams.
Yes.
We do have assignment due on October the 6th, okay, which is on exercise number 8 from chapter 1. Okay, that's for today. I'll stop the recording.